In this short video, we're going to go back through the two types of acids and bases that you've already studied, add a quick third one, and also add in a little bit of history about pH. You will recall Arrhenius. He was the first one we studied. Notice the date, 1884. He had the idea that acids produce H pluses and bases produce OH minuses in water, and that was the limitation of his theory. He also did a lot of things with how ionic compounds dissociate, so that kind of makes sense why he'd come up with this. One of the things you don't know is that Sorensen in 1907 came up with the pH scale. Up until that time, there were two ways of measuring acidity, not basicity. We don't really measure basicity, we measure acidity. And one was the conductivity of a current through a solution, and the other is, what color did it turn the indicator. So these were all they could do up until 1907 to measure how acidic something was. In 1907, he developed the pH scale. So little p, big H, and we got this equation, the negative log of the H plus concentration. That's what those brackets mean. The P comes from the French, and it means power. What you're going to find is that anything with a P in front of it actually means the negative log of that thing. And fortunately, it is the log base 10, so no fancy math here. And we'll get to that in the next lesson. Back to our old friends, Bronsted and Lowry in 1923. Remember, they worked at the same time but not together and came up with this idea that acids were proton donors and that bases were proton acceptors. This doesn't have to be done in water, it just has to have a proton to donate or accept. And this is the definition we'll use the most. You'll be tested on this. This one really works well for chemistry up until organic chemistry. And we actually need this guy's definition for organic chemistry. Lewis. You should know a Lewis dot structures. All about the electrons, right? Well, Lewis looked at acids and bases, and he said, wait, acids are electron pair acceptors. That's not contradictory to Bronsted and Lowry, because if you think about it, if you donate your proton, didn't you just accept the electrons? So you got rid of the proton, now you've got electrons. A base is an electron pair donor, so it used to gain the proton, but now it's actually allowing that proton to stick to it. You can think of it that way. Or you can look here and see that NH3 donates its protons to BF3. Here's the bond. And that happens in the Lewis acid-base reaction. This is the acid because it accepted the electrons. This is the base because it gave the electrons for this. This one is very confusing if you ask me, and really it's great for when you get to organic chemistry. Now, just to kind of look at it holistically, what you can see in this diagram is that Lewis encompasses all acids and bases, and Bronsted and Lowry encompasses a great number of acids and bases, but those also can be considered Lewis acids and bases. Very narrow is Arrhenius, and that's because it requires water. So every acid and base that we would say, oh, that's an Arrhenius acid and base, is also a Bronsted-Lowry and also a Lewis. Everything that we would say is a Bronsted-Lowry acid and base is also a Lewis acid and base. So Lewis encompasses all acids and bases, and you need to know the definition, and you need to know it is the broadest term, or broadest definition rather, and Arrhenius is the most narrow. Let's see if I can fit narrow in here.